Good morning and welcome to our fourth lecture. Today we're going to talk about vectors, dot product and cross product. First I'm going to talk about vectors. Some quantities, for example mass, or time or distance, only need a number to describe the quantity. 10 kilograms, 5 seconds, etc. For some quantities, for example velocity or force, we need both a number and a direction. A vector is an object which has a size and a direction. We can imagine a vector as an arrow. The length of the arrow tells us how big the vector is, the size of the vector, and the direction that the arrow is pointing in tells us the direction of the vector. If we have an arrow like this, which starts at the point A and ends at the point B, we can write this as AB with an arrow over the top. The starting point of the arrow is called the initial point. The ending point of the arrow, where the arrowhead is called the terminal point. We can write the length of the vector using these double vertical lines. Double vertical line, AB arrow, double vertical line is the length of the vector AB. We say that two vectors are equal if they have both the same length and the same direction. They don't have to have the same initial point or the same terminal point, but they need to have the same length and the same direction. If we look at this picture, we can say that the vector AB is the same as the vector CD. These two vectors have the same length and they have the same direction. Therefore, we can write AB is equal to CD. Likewise, EF is the same vector and OP is the same vector. Note that AB and GH are not the same vector because the lengths are different. Here's AB, here's GH. GH is longer than AB, so these vectors are not the same. We could also say that AB and IJ are not the same vector because the directions are different. Let's briefly talk about notation for vectors. When we use a computer, for example, these slides or the lecture notes, we usually use bold letters for vectors. For example, bold U, bold V, bold W are vectors. If we write mathematics with a pen, it's difficult to use bold letters, so instead we use underlined letters. For example, underlined U, underlined V, underlined W are vectors. So for example, if I'm using a computer and you see AU plus BV, or if I'm using a pen writing on paper and you see A underlined U plus B underlined V, then A and B are numbers, U and V are vectors. We're going to be talking about vectors in both two-dimensional space and in three-dimensional space. In two-dimensional space, if V has initial point 0, 0 and terminal point V1, V2, then we can write the component form of V as V is equal to open bracket V1 comma V2 closed bracket. And let me briefly talk about notation again. This V which I'm pointing at the moment is a vector. This is bold. V1 and V2, these are not in bold and they're not underlined. These are numbers. If we're in three-dimensional space, we have the same idea. If V has initial point 0, 0, 0 and terminal point V1, V2, V3, then the component form of the vector V is open bracket V1, comma V2, comma V3, close bracket. This is a picture of a vector in three-dimensional space. Remember that for the coordinates, which we talked about last week, the x-axis, the y-axis, and the z-axis, we understand the way that these are pointing using our left hand. Counting from the bottom, this finger points in the direction x, this picture finger points in the direction y, so therefore the thumb points in the direction z. This vector has initial point P and terminal point Q. So the vector V can be written as the vector from P to Q. We can write the component form as V1, V2, V3, and we can calculate that this is x2 minus x1. How does the x coordinate change? And how does the y coordinate change? y2 minus y1. And how does the z coordinate change? z2 minus z1. The norm, which is a mathematical way of saying the length of a vector, is given with this formula. The norm of the vector v is square root of v1 squared plus v2 squared. In three-dimensional space, we have a formula. Now we have three coordinates. The norm of the vector v from p to q in the previous picture is the square root of v1 squared plus v2 squared plus v3 squared. Or if we have coordinates as in the previous picture, that's the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. We have zero vectors. The vector bold 0 means zero vector, and that's the vector with component form 0, 0 in two-dimensional space or 0, 0, 0 in three-dimensional space. Note that when I write 0 in bold, I mean a vector, zero vector. If I don't use bold or I don't use underlined, then these zeros are just the number 0. The norm of this zero vector is the number 0. Bold 0 is a vector, normal 0 is a number. If we have a vector which is not the zero vector, then we know that the norm of the vector is always strictly positive. That's because with square root, we always get a positive number. For example, find the component form of the vector with initial point minus 3, 4, 1 and terminal point minus 5, 2, 2. We're trying to find this vector v, which starts at p and ends at q. What we do is we calculate terminal point minus the initial point. We calculate q minus minus 5, 2, 2, minus 3, 4, 1. For the first numbers, minus 5 and minus 3. Minus 5 minus 3 is minus 5 plus 3, or minus 2. In the second position, 2 minus 4 gives minus 2, and in the third position, 2 minus 1 gives 1. And then part B, find the norm of the vector. We have our formula. The norm of V is the square root of V1 squared plus V2 squared plus V3 squared. If we put these numbers in, square root of minus 2 squared, which is 4, plus minus 2 squared, which is 4, plus 1 squared. 4 plus 4 plus 1 is 9, and the square root of 9 is 3. The vector minus 2, 1 has norm equal to 3. Briefly, I want to talk about how we can imagine adding two vectors together. There are two ways to think about this. In the left picture, we might think about putting the vectors nose to tail. Suppose I have a red vector u, and at the terminal point of u, we also make this the initial point of v. We start just here, we end at the top. Green vector u plus v starts at the initial point of u, and it ends at the terminal point of v. There's another way to think about adding two vectors together. You might imagine that they start at the same initial point. In the right-hand picture, the red and the blue vectors have the same initial point. We can draw a parallelogram with this dotted line, and then the green vector, u plus v, has the same initial point as u and v, and it has a terminal point at the opposite corner of parallelogram. We can multiply vectors by numbers. For example, if the red vector is the vector u, I might multiply this vector by the number 2, get the vector 2u. 2u and u point in the same direction. The length of 2u is double that of u. Or I might look at 1.5 multiply u, or 0.5 multiplied by u. These two vectors, u and 0.5u, point in the same direction. The length of 0.5u is half that of the length of u. We can also multiply vectors by negative numbers. For example, I might multiply u by minus 2. The vector minus 2u has the same length as 2u. Because of the minus sign, it points in the opposite direction. You can also subtract vectors, and there's two different ways to think about this. In the left picture, if we imagine that u and v have the same initial point, we can complete the triangle. This vector is u minus v. Or we can think about this in a different way. Instead of thinking about u minus v, we can think about u plus minus v, because u plus minus v should be the same as u minus v. And we can use the nose to tail rule from 2 slides before. Take the vector u, where u has terminal point, the initial point of minus v, and then draw the green arrow from the initial point of u to the terminal point of minus v. So u plus minus v. And of course, you can see from the picture that u minus v is the same as u plus minus v. Now, let's suppose we have two vectors in three-dimensional space, u and v. And let's k be a number. Then we can calculate u plus v. All we're doing is we're adding together the components. The first component, u1 and v1, we add together. In the second position, we do 2 plus v2. And in the third position, we do u3 plus v3. If we multiply a vector u by a number k, then all we're doing is we're multiplying each coordinate or each component of u by the constant k. So ku1, then ku2, then ku3. Now I want to talk about the norm of ku. Start with the norm of ku. This is a vector, so I'm using these double vertical lines. This is the norm of the vector ku1, ku2, ku3, and using the formula, this is the same as the square root of ku1 all squared plus ku2 all squared plus ku3 all squared. Which of course is the same as the square root of k squared u1 squared plus k2 u2 squared plus k squared u3 squared. We can factor out the k squared, and then we can take this outside of the square root. Because the square root of the product of two numbers, let's say square root of ab, is the same as the square root of a, square root of b. We have the square root of k squared, which is the same as the absolute value of k, multiplied by the square root of u1 squared plus u2 squared plus u3 squared, which is the same as the norm of u. So the norm of ku is the same as the absolute value of k multiplied the norm of u. U is a vector. For a vector, we use double vertical lines. Remember, k is a number. The size or the absolute value of a number, we use these single vertical lines. The vector minus u, which is the same as minus 1 multiplied by u, has the same length as u, but it points in the opposite direction. For example, let u be minus 131, and let u be 470. And we're asked to find 2u plus 3v. Here's the calculation. 2 times minus 131 plus 3 times 470. Multiply the vector by its constant to get minus 262 and 12.10, and then add them together to get 10.27. Find u minus v. Minus 131 minus 470. We do the substitution each coordinate to get minus 5 minus 4, 1. And then finally, calculate the norm of a half u. As we did on the previous page, if we have a number inside the norm, we can take the number outside. If the half is a positive number, we don't need the absolute values around. We can just say that the norm of a half u is equal to a half multiplied by the norm of u. And then when we run through the calculation, we get a half square root of 11. We use the answer like this. Don't bother using a calculator to calculate the square root of 11. Anybody in the world who has a calculator can do that. If you're interested in the difficult bit, the actual maths. Anytime you do homework or an exam, leave your answer looking like this. If you have a square root of a number, just leave it as a square root of a number. Briefly, let's go through some properties of vector operations. Number one, u plus v is the same as v plus u. Doesn't matter which order of vectors together. Likewise, if we have two vectors, we added u plus v first and then added w. That's exactly the same as adding plus w first and adding on u. U plus the zero vector is equal to u. U plus minus u is of course the zero vector. 0 multiplied by u is equal to 0. Now note just here I'm using two different zeros. The 0 on the left is a number, and this 0 on the right is the zero vector. The number 1 multiplied by u is of course just u. If a and b are numbers and u is a vector, then a multiplied by bu is just the same as ab multiplied by u. Doesn't matter which order we multiply these together. A multiplied by u plus v is just au plus av, and a plus b multiplied by u is au plus bu. We can add and subtract vectors, and we can multiply a vector by a number. What we can't do is we cannot multiply vectors. Don't write vector u multiplied by vector v because this is meaningless. Unit vectors. A vector u is called a unit vector if and only if the norm of u or the length of u is equal to 1. For example, this vector 2 to the power minus a half, which is the same as 1 divided by the square root of 2. A half minus a half is a unit vector, because if we calculate the norm of u, we get equal to 1. I'll leave this for you to check. I'm just going to go ahead quickly. In two-dimensional space, we have two standard unit vectors, which we call I and j. I is the vector 1, 0, and j is the vector 0, 1. In three-dimensional space, we have three standard unit vectors, which we call I, j, and k. A vector in three-dimensional space can be written in terms of I, j, and k. If we had the vector with component form v1, v2, v3, this is exactly the same as the vector v1i plus v2j plus v3k. We put the first component next to I, the second component next to j, the third component next to k. Two different ways to write the same vector. Now, if v is not the zero vector, in other words, if the norm of v is not 0, then we can calculate v divided by the norm of v. V is a vector, norm of v is a number, so it's okay to do vector divided by number. And I'm claiming this is a unit vector. To show this, I'm going to calculate the norm of v divided by the norm of v, which is the same as the norm of the number 1 divided by norm v multiplied by v. Now you will remember that if we have a number multiplied by a vector and we take the norm, That's the same as the absolute value of the number multiplied by the norm of the vector. Using this rule, we can take 1 divided by the norm of v outside of this norm. And because this is a positive number, we don't need to worry about absolute value symbols. We just get 1 divided by the norm of v multiplied by the norm of v. But of course, this is just equal. So we have these two vectors, v divided by the norm of v and v, and they might look like in this picture. They point in the same direction. The norm the orange vector has length 1. The orange vector is a unit vector. Anytime we have a non-zero vector and we want to create a unit vector pointing in the same direction, we use this idea. We take our vector and we divide by the norm vector. Here's an example. Find a unit vector u which points in the same direction as p1 and p2. First of all, we need to calculate p1, p2. I'll leave this for you to check. We do the terminal point minus the initial point, p2 minus p1, and we calculate this as 2i plus 2j minus k. We could also calculate the norm of this vector, and you can check the norm is equal to 3. So, using the idea from the previous page, we have a vector p1, p2, and we want to find a unit vector which points in the same direction. So what we do is we take a vector and we divide it by its norm. In other words, we have the vector 2i plus 2j minus k, and we're going to divide by the number 3. We get 2/3 I plus 2/3 j minus 1/3. And I'll leave it for you to check that this is a unit vector. Chapter 12 is about dot product. First of all, in two-dimensional space, if we have two vectors u and v, we can have the dot product of u and v, u dot v. This is defined to be u1 v1 plus u2 v2. Remember, I said we can't multiply two vectors together, but we can do this thing which is called a dot product. It's different from multiplying two vectors together. And in three-dimensional space, we have the same idea. The dot product of u and v, u1 v1 plus u2 v2 plus u3 v3. We're going to be using these formulae in this chapter. If we have two vectors, we can use the dot product to calculate the angle between two vectors. The formula to remember is this angle theta is inverse cosine of u dot v divided by the norm of u, norm of v. Let's go through some examples. The dot product of 1 minus 2 minus 1 and minus 6 to minus 3. First, we take first numbers, 1 and minus 6, and multiply these together. 1 multiplied by minus. Then we take the second numbers, minus 2 and 2, and we multiply them together. And then thirdly, we take the third numbers, minus 1, minus 3, and we multiply these together. And then we add these three numbers together. Minus 6 plus minus 4 plus 3 gives us the answer. The dot product of these two vectors is minus 7. Or we can do a half plus 3j plus k, dot product with 4i minus j plus 2k. Again, we take the first numbers, it's a half and 4, blend together. We take the second numbers, 3 and -1, and we multiply that. And the third numbers, 1 and 2, and multiply these together. We get 2 minus 3 plus 2, or 1. We can use the theorem from a few slides ago to calculate the angle between this vector u and this vector v. Here's our formula. The angle is inverse cosine of u dot v divided by the norm of u, norm of v. So we need u dot v, we need the norm of u, and we need the norm of v. I'll leave this for you to check. We can calculate that u dot v is -4. We can calculate that the norm of u is 3, and we can calculate that the norm of v is equal to 7. Put these numbers in, calculate inverse cosine of 4 divided by, sorry, of -4 divided by 3 multiplied by 7. And if we have a calculator, we can see this is the same as 1.76 radians, or 98.5 degrees. Another example. Let's suppose we have a triangle ABC, and we're asked to calculate the angle theta, which is the angle at C between the sides AC and the side CB. What we need to do is we need two vectors. We need the vectors from C to A, and we need the vector from C. And then we're going to use the formula to calculate the angle between these two vectors. Theta is the angle between the vector CA and the vector CB. We can run through our calculation. I'll leave this for you to check later. And then we can use the formula. The angle is inverse cosine of CA dot CB divided by the norm of CA and the norm of CB. I'll leave this for you to check that when we calculate this, we get 78, approximately, I should say, approximately 78.1 degrees. Definition. Two vectors are orthogonal if and only if their dot product is equal to the number 0. Now, you will remember we had a formula for the angle. The angle was inverse cosine of u dot v divided by norm of u, norm of v. If we rearrange this formula, we can also write this as u dot v is norm of u, norm of v cos theta. Therefore, we can say u and v are orthogonal. Orthogonal means the dot product is equal to 0. How is this equal to 0? How do we get equal to 0 here? Maybe the norm of u is equal to 0. In other words, u is a unit vector. Maybe the norm of v is equal to 0. In other words, v is the 0 vector. Or maybe cos theta is equal to 0. How do we get cos theta equal to 0? We have to have an angle of 90 degrees. For example, the vectors 3 minus 2 and 4, 6 are orthogonal because if we calculate the dot product of these two vectors, we get 0. And these two vectors are orthogonal as well. I'll leave it for you to check that. If we calculate u dot v, then again we get 0. The 0 vector is orthogonal to every vector u because if we're in three-dimensional space, 0 vector u dot any vector u is 0, 0, 0 dot u1, u2, u3. Take the first numbers, 0 and u1, multiplied together. 0 multiplied by u1, of course, is just 0. And then the same in the second position. 0 multiplied by u2 is 0. And in the third position, u multiplied by u3 is 0. So, of course, we just get 0. Some properties of the dot product. Let's suppose we have three vectors u, v, and w, and some number k. And it doesn't matter which order we do a dot product in. U dot v is the same as v dot u. It doesn't matter when we multiply by the number k. Ku dot v is the same as u dot kv, or k by u dot v. If we have numbers, you'll remember that a multiplied by b plus c is, of course, a plus ac. We have the same idea for dot product. U dot v plus w is the same as u dot v plus u dot w. As long as you remember the formula for numbers, you can remember that we can do the same thing for vectors. U dot u is the same as the norm of u squared. I'll leave this for you to think about. And 0 vector dot u is the number 0, as we saw on the previous slide. Vector projections. Projections is something we're going to be using a lot next week. We're going to do the first type of projection now. If we have two vectors u and v, we can project one vector onto the other vector. Two ways to think about this. Let's suppose v is the ground, and let's suppose that we have some vector u which is sticking out of the ground made of metal. And let's suppose that we have the sun up here. We can ask, where is the shadow of u on top of v? And the answer is the shadow of u is this vector, blue vector, which we call the projection of u onto v. There's another way to think about vector projection. Is we might imagine that we're squashing one vector onto another one. Let's suppose we have something heavy which comes down and it squashes u straight down onto v. Imagine u being squashed down like this until u is level with v. Again, the vector projection of u onto v. In mathematical language, vector projection of u onto v is the part of the vector u which points in the same direction as v. In these pictures, and I've been talking about the left picture, but the right picture is also true if, for example, the angle between u and v is more than 90 degrees. In these pictures, the projection of u onto v is the vector from P to R. Now, the projection of u onto v, it points in the same direction v. In other words, it points in the same direction as a unit vector, points in the same direction as v. And we can calculate the projection of u onto v as a number, its length, multiplied by its direction. The direction we can use a unit vector. For the length, we use the norm vector. Looking at this picture now, we can see that the length of the blue vector is the norm of u cos theta. So here we are. The length of this vector is the norm of u cos theta. How do we get a unit vector which points in the same direction as v? We've talked about this. If we want to create a unit vector points in the same direction as v, we have v divided by the norm of v. And as we run through this calculation, we find a formula for the projection of u onto v. U dot v divided by the norm of v squared multiplied v. This is an important formula. We're going to be using this a lot next week, so please make sure you memorize this before next week. For example, find the vector projection of the vector 6 plus 3j plus 2k onto the vector I minus 2j minus 2k. I'll leave this for you to check. If we used our formula which I said you need to remember, if we put all the numbers in, we calculate a vector. The answer should be a vector. Minus 4 over 9i plus 8 over 9j plus 8 over 9k. As I will leave for you to check later when you read the lecture notes. Or another one in two-dimensional space, find the vector projection of vector f onto the v. Use the formula, put the numbers in. I'll leave it for you to check that we get minus 1 over 10i plus 3 over 10j. I'm going quickly here because when you re-watch the video or the lecture notes, you can spend more time if you need to. Our final chapter for today is about the cross product. This is another way to combine two vectors. As I said, we can't multiply vectors, but we do have a dot product to combine two vectors, and we have a different way to combine two vectors called the cross product. Let's suppose we have two vectors, u and v. And let's suppose we're using our left hand to describe the position of these vectors. Let's suppose we use our second finger to describe the direction of the vector u. Hold your hand so that your second finger points in the same direction as u. Hold your hand so that your first finger points in the direction v. And then your thumb, assume that this angle is 90 degrees, will tell us the direction of a new vector n. This new vector n must be a unit vector, and it must satisfy three rules. First of all, n must be orthogonal to u. In other words, the angle between u and n must be 90 degrees. N must also be orthogonal to v. Angle between n and v must be 90 degrees. And we must use our left hand to decide the direction n. Go back to the picture. Use our left hand, always our left hand. U on the second finger, V on the first finger, N on the thumb. These angles must be 90 degrees. And then our thumb tells us the direction of the vector N. And then we're ready to define the cross product of U and V. Let me remind you first of all, U dot V, we know is the same as the norm of U, norm of V, and then cos of the angle between u and v. We have a similar formula for cross v. It's norm of u, norm of v. Now instead of cos we have sine, and one more difference, we multiply by a unit vector n. There's an important difference between a dot product and a cross product. U dot v is a number, u cross v is a vector. We can also say u and v are parallel and only if the angle between them is 0 or 180 degrees. U and v point in the same direction, and the angle between them is 0 degrees. If they point in opposite directions, then the angle between them is 180 degrees. This is what parallel means. But sine of 0 and sine of 100 degrees are both 0, which tells us that if u and v are parallel, then u cross v must be a 0 vector. We have some properties of the cross product which I want to run through. If we have two numbers, r and s, and two vectors, u and v, and we do ru cross sv, that's the same as rs multiplied by u cross v. U cross v plus w is as we would expect. But this one perhaps looks a little bit unusual. V cross u is equal to minus u cross v. I'm going to discuss this in a moment. Property 4 looks straightforward. V plus w cross u is v cross u plus w cross u. Yeah, I'm happy with that, and that makes sense. 0 vector u cross u is always equal to the 0 vector, as you can see from the definition. And another unusual one, u cross v cross w is u dot w v minus u dot v w. Let's talk about property 3. Remember that we use our left-hand side direction of n, and therefore the direction of u cross v. In the left picture, n must point upwards if we hold our left hand like this. So u cross v is this orange vector. Let's suppose instead we look at the right. U and v are the same vectors. Now I want to do v cross u. That means on my second finger now I need this to point in the direction v, and I need my first finger to point in the direction u. If we hold our hand this way, now our thumb points downwards. In other words, n must point downwards, or the vector v cross u must point downwards. Compare these two pictures together. U cross v points upwards, v cross u points downwards. We point in opposite directions, therefore v cross u minus u cross. We can use the cross product to calculate the area of a parallelogram. Suppose I have this blue parallelogram, and I know that the vector u and the vector v point along one side of the parallelogram. We know that the height of the parallelogram using trigonometry is the norm of v sine theta. So the area of the parallelogram, that's base multiplied by height. Base is the norm of u. height, or h, is norm v sine theta, and you will note that this is the same as norm of u cross v. Anytime we have a parallelogram like this, and we already know u and v, and we're asked to calculate the area, our formula is that the area is the norm of u cross v. Or we could do the area of a triangle. And this is straightforward. You can see from the picture that the area of this blue triangle is a half of the area of the parallelogram that we just spoke about. So the formula for the area of a triangle is a half norm of u cross v. We'll do some examples of triangles later. But first, we need a formula for u cross v. And we're going to do this in terms of I, j, and k. So here's I, here's j, here's k. I want to first know that I cross I is 0, of course, because I and is parallel to itself, therefore the angle is 0 degrees and sine of 0 is 0. Similarly, K cross j is 0 and k cross k is 0. Next, I want to talk about I cross j. Go back. Look at this picture. Imagine you hold your left hand in front of this picture. Hold your left hand so that your second finger points in the direction I and your first finger points in the direction K. You try and draw a really bad picture of a hand. Second finger should point in the direction I. First finger should point in the direction J. And therefore, thumb should point in the direction I cross J. On this picture, where is the thumb pointing? The thumb is pointing upwards in the same direction as K. So we can say that I cross J must point in the same direction as K by the left-hand rule. And then we can calculate norm of I is 1, norm of J is 1, sine 90 degrees 1, 1 multiplied by 1 multiplied by 1 multiplied by K, which of course is just K. Then immediately, J cross I must be minus IJ or minus K. We can do the same thing for J cross K, K cross J, I cross K, and K cross I. I'm going to leave this for you to think about. Go back to the picture 2 slides before and hold your hand in front of the picture with your fingers pointing in the particular directions and look to see which direction does your thumb point in. Now we're ready to calculate u cross v for general u and general v. I'm going to do u1i plus u2j plus u3k cross v1i plus v2j plus v3k. We multiply these out in the obvious way. First of all, u1i cross v1i gives u1 v1i cross I. And then we do u1i cross v2j, which gives u1 v2i cross j. You can also do u1i cross v3k. That's u1 v3i cross k, etc. If we multiply these out, we get 9 terms. And then we can look to simplify. I cross I is 0, so we don't have this. Forget about this. J cross J is also 0. Forget about this. K cross K is 0. Forget about this. Instead of 9 things to think about, we only have 6 to think about. I cross j we know is k. I cross k we know is minus j, etc. These on the previous, replace these, and then simplify. We get our formula u2v3 minus u3v2 I minus u1v3 minus u3v1j plus 1v2 minus u2v1k. This is the formula for the cross product. Make sure you make a note of this for homework questions. Let me write this as in terms of a theorem, because this is an important formula to remember. U cross V is given by this formula. I don't want to take a break because I'd like to finish. I've only got 10 minutes or so to finish, and then you can leave whenever you wish. I'm going to finish in about 10 or 15 minutes rather than taking a break. If you studied matrices and determinants at high school, then there's another formula for determinant that you might wish to use. U cross V is the determinant of this 3x3 matrix or pseudo matrix IJK U1 U2 U3 V1 V2 V3. If you understand this, you're welcome to use this in the exams. If you haven't studied this already, doesn't matter, just use the formula on the previous page. For example, find U cross V and V cross U if U is 2ij plus k and V is minus 4i plus 3j plus k. Use our formula, and I'm going to leave this for you to check. If we put the numbers in the formula, we get minus 2i minus 6j plus 10k. The formula is U2 minus V3 I. Write that again. It's U2 V3 minus U3 V1 I. U2 V3 is 1 multiplied by 1, or 1. U3 is 1. V1 is minus. So V2. U3 is 1. V2 is 3. 1 multiplied by 3 gives 3. 1 minus 3i. And then the same for the rest of this, which I will leave for you to check. And then the second one is easy. V cross U is minus U cross V. We don't need to do the long calculation. We can just use this rule. And we can say that they are 2i plus 6j minus 10k. For example, find a vector perpendicular to the plane containing the 3 points P, Q, and R. What we're going to do is we're going to write down the vector from P to Q and the vector from P to R. And then we're going to find a vector which is perpendicular to both of these vectors. We have these two vectors, and we want to find a new vector which is perpendicular to both of them. This is just the cross product. The cross product is always perpendicular to these by definition. The vector PQ cross PR perpendicular to the plane because this vector is perpendicular to PQ and this vector is perpendicular to PR. So what we do is we calculate PQ is I plus 2j minus k. Calculate PR is minus 2i plus 2j plus 2k. And then we use the cross product formula to calculate PQ cross PR is 6i plus 6. And this is the answer. Vector 6i plus 6k is perpendicular plane. Find the area of this triangle. This is exactly the same P, Q, and R as in the previous example. We talked about the area of the triangle. Area of the triangle is half multiplied by the norm of PQ cross PR. We've already calculated this. We've already calculated PQ cross PR is 6i plus 6j. So to calculate this area of this triangle, all we're doing is a half multiplied by the norm of 6i plus k. And you can check that this is 3 square root of 2. Find a unit vector perpendicular to the plane containing P, Q, and R. Exactly the same P, Q, and R as before. We've already found a vector P, Q cross PR, which is perpendicular to this plane. Now we need to find a unit vector which points in the same direction as PQ cross PR. Remember how we find a unit vector which points in the same direction as a vector? We just take the vector and we divide by its norm. So what we're doing is we're doing our vector 6i plus 6k, and we're going to divide by its norm, which calculated on the previous example, is 6 square root of 2. We have the unit vector 1 over root 2i plus 1 over root 2k. Here's an interesting example. We have a 2 by 2 by 2 cube, and inside the cube is drawn a triangle. Use the cross product to find the area of the triangle. To use the cross product, we need 2 vectors. And to have 2 vectors, we need to have coordinates. We need to put our x, y, z axes on this picture. And we can put them anywhere we want. I choose to put the origin 0, 0, 0 at the back of the. I choose to have x pointing in this direction, y pointing in this direction, and z pointing in this direction. You can draw your axes wherever you want. To me, this makes the most sense to draw the axes in this way. After we've drawn the axes, we can write down coordinates for the corners of the triangle. This corner is on the x-axis and has coordinates 2, 0, 0. Coordinate is on the z-axis and has coordinates 0, 0, 2. And the third corner of the triangle is in the xy plane, so the third position is 0. And because the side of the triangle is 2, this has coordinates 2, 2, 0. Then we can proceed as we did before. We have a triangle and we know the coordinates of the corners. We can find 2 vectors. We're going to find the vector AB and the vector AC. Their cross product, and then the area will be half of the norm of their cross product. So, first of all, AB is 2j, and AC is minus 2i plus 2k. As you can check, then we can calculate AB cross AC. If you understand determinants, you might use this formula. If you don't understand determinants, then use the formula which I've given in the lesson earlier today. I multiplied by u2v3 minus u3v2, or 4 minus 0, minus j multiplied by u1v3 minus u3u1, or minus 0, plus k multiplied by u1v2 minus u2v1, which is 0 minus minus 4. And when we calculate this, you can check, we get 4i plus 4k. Therefore, we can use our formula. Area of a triangle is half multiplied by the norm of AB cross AC. Put the numbers into this, calculate the norm. We can find that the area of this triangle is 2 square root 2. Final idea for today is the idea of the triple scalar. This is a way to use both dot product and the cross product. Scalar product of v and w, and in this order: first u, second v, third w. Triple scalar product is u cross v dot w. Now, let's think about this. Does this make sense? U is a vector and v is a vector. We can do the cross product between two vectors and we get a vector. Okay, w is also a vector. We have vector dot vector. When we do vector dot vector, we get a number. A three-dimensional object like this is called parallelepiped. Suppose we have a parallelepiped where the vectors u, v, and w lie along edges of parallelepiped. Then we can calculate the volume of the parallelepiped. The volume of a parallelepiped is the area of the base multiplied the height of the parallelepiped. Area of a base, we already know the area of a parallelogram is the norm of u cross v. Using trigonometry, we can find the height is the norm of w cos theta. Multiply these together, and what do we have? We actually have the absolute value of the triple scalar product of u, v, and w. One final comment before I finish. Dot product we can do in both two-dimensional space and three-dimensional space. Let me warn you, there is no cross product in R3. To be able to do the cross product, we need to use our left hand. We need to hold our left hand up, use our fingers to decide on the direction of u cross v. We can only do this in three-dimensional space. We can only do the cross product in three-dimensional space. We cannot have cross product two. And that is the end of today's lesson. Next week, we're going to finish our discussion of the geometry of space. The final three chapters about geometry are lines, planes, and projections. Do you have any questions? The exam will be in week 9. This will be announced by the architecture department when it's finalized, but it will probably be in the time we normally have a lesson in week 9. So if I remember rightly, that's the 4th of November or the 5th of November, Friday morning at 9 o'clock. Let me check my calendar. I mean December, of course. Not November, December. 4th of December, probably at 9. At the moment, this is only 99% set. Keep an eye out for announcements from the architect department because there's a small possibility that might change. Okay, so as I said, this is the end of the lesson. You are welcome to leave whenever you wish. If you have questions, you can ask me. If you think of a question later, you can ask to me via the board. I'm going to 10-minute break, and then I will come back to see if there are any more questions. If you don't have questions, you're welcome to leave now if you wish.